It's fun to be in a cross-disciplinary group. So basically, I mostly talk to economists and sociologists, and then to talk to people that often are subjects of our studies is actually really, really fun. Stanford, just as a personal note, Stanford is near and dear to my heart. My mother in the 70s left Pakistan to come to Stanford to do her master's degree. And that enabled us to immigrate in the early 80s to Canada. And it was really the Stanford education that really set us up for where we are today as a family. And it's always had a soft spot in our hearts. And of course, when I was considering graduate school, Stanford was on the top of my list. And somehow MIT kept winning over every single time. But I'm super happy to be here and to present this work. This work is in collaboration with Kevin Boudreau, my good friend and co-author at the London Business School. We went to MIT together as PhD students and have started to work together on a bunch of these kinds of questions. And so what I'm going to talk about, you saw the title, I keep changing the title around to make it more simpler. So this is the new title, how disclosure policies impact search and open innovation. I'm going to explain to you all of this as we move forward. I just want to give you a sense of my research and how it all fits in. I've really been thinking a lot about how crowds get organized and how we can get productive work from crowds. And there are really two major institutions that we see out in the economy that enable us to work with crowds. The first setup is competitions and contests. And in this work, I've done a bunch of work to sort of explain who wins and why, what are the bases for performance in these settings, why people participate, and behavior in contests. And I've done both research using archival data, looking at Innocentive and Topcoder to pull out these results, and also field experiments. And we'll walk you through a field experiment soon. The other way to set this up is actually through a community. So everybody's aware of the open source software world and what that's done. And I've, in fact, started my research first there to say, how does open source work and why does that actually produce such robust quality software? And again, I've looked at issues about motivation, self-selection, and participation, and now doing increasingly more work around partner selection and for collaboration through field experiments as well. And in many ways, these two institutions are diametrically opposed if you sort of think about it. In the one case, you're basically running a winner-take-all contest where people are competing and rushing to solve a problem. And in the other setting, you have communities. People are sharing knowledge, they're learning from each other, and they're collectively improving the overall perspective of the code being produced and the overall performance of the code being produced. And for me, this has always been a puzzle in terms of what's the better way to organize ourselves? Should we, when we have a creative task, when we have a software programming task, when we have a scientific task, is it better for us to set up ourselves in communities and collaborations, or is it better for us to set up contests and competitions? In many ways, I started here. This I was actually kind of allergic to when I first started paying attention to this during my dissertation time, because I drank the open source Kool-Aid, and I just felt like that was just a great way to organize work. But as these became more and more popular and powerful, it required attention to say, like, what's going on here, and why are these equally as effective as this? And that's what the puzzle I'm going to try to solve over the next time we have. The work I do is part of what's called the NASA Tournament Lab. It's a research lab funded by NASA to help us understand how these types of open innovation perspectives can be put to use for government agencies, but for innovation in general. And so what we do is we work with NASA, we take their toughest computational challenges, and then we crowdsource them through platforms like Topcoder. I've also done a bunch of work with our medical school in the computational biology side of things, where again saying that in fact we can take computational biology questions and also get them solved through contests and communities. And in addition, a bunch of work, let me just hang on a second, and a bunch of work around how we actually organize collaborations in the medical school setting. So if you look at the Harvard Medical School, we have 20,000 researchers, about $1.5 billion in funding from the NIH, and three campuses that are far apart from each other. How we find collaborators and partners is actually a big, big question here, and that's part of our research agenda that we also pursue. So let me give you an example first of a contest we recently ran for NASA for the space station. So let's have a look.
Energy, in one form or another, powers everything on Earth, and the man-made things floating above it, too. This is the International Space Station. You've probably heard of it. It's powered by the sun, and the sun's energy is captured by the station's solar panels. Ensuring the space station harvests the most energy possible is a complicated task. Why? Well, for one reason, see those large solar panels? Holding them to the station are very long, thin arms called longerons. Anytime an odd number of longerons are in full sunlight, with others in the shadows cast by the rest of the space station, they bend and eventually break. For this reason, ISS operators are careful to position the station to limit shadowing, and so only an even number of longerons are shadowed at one time. However, this conservative positioning reduces the power the station can collect from the sun, thus causing inefficiency. NASA wants more power for the ISS. More power means more science and cool stuff that NASA can do on orbit. NASA needs a sophisticated algorithm, and they think you just might be the key to this whole equation. Introducing the NASA Tournament Labs International Space Station Longeron Challenge. Your solutions just may help power the International Space Station and allow more science from more scientists around the world. Consider this your invitation to blast off with NASA. For more information, visit topcoder.com/ISS if you've got the right stuff.
So this ran in March, 30K pool of cash available to solve this problem. It was a 3-week-long contest. Here's what we got. We had broad engagement, 459 competitors submitting about 2,000 code submissions. We had actually had 2,000 signups. It was quite incredible. NASA can be a big draw for people to participate. The winners are here. So Italian, Chinese, Polish, Chinese, Estonian, Chinese, Canadian, Chinese, and Belarusian.
We clearly need to be trained better.
Yes, exactly. What are you guys doing about it? So this, so we get broad engagement and really cool code. Of course, NASA cares about how good is the code, right? Does it actually do anything at all? And what we have here for you is the final output of the code submissions that they had for how much power output you can get based on the configurations that they predicted. And this is sort of solar power output, and then this is every single person that had submitted in their final submissions. Now, some things you'll see immediately is that there's actually quite a bit of bunching, right? People have done really well. And in many ways, sort of the differences between the first and second are not that great. But then here's the NASA solution, okay? And depending upon how you model the NASA solution versus our solutions, we either exceed or meet what they've done, all right? So in what was, multi-year, multi-X millions of dollars of projects that they do to get this kind of information out, we were able to basically get done in 3 weeks for 30K. And this becomes a very compelling way for us to think about organizing creative work if we can actually take these very tough software problems that require lots of people and lots of attention and say, can we actually get it done this way?
So how do you choose 30K?
Random. So in fact, that's a good question. The prize size is in fact still an art than a science. What we're finding is that too high a prize, and that'll actually deter entry because people think the problem is too hard. But you want to actually reward people for their efforts as well. So we've been typically in these types of projects in the 10 to 50K, depending upon the problem and what we're trying to get done on the back end side. In terms of the reward size?
Yeah.
That's on the high end for top coder. Top coder projects are typically much smaller than that. They'll be like $500 or $1,500, but those are for more software components. These are longer term projects, 3 weeks, 4 weeks, and so on. Of course, as we'll discuss later, there's beyond just the prize money here. Get your code assessed by NASA, having your name on the wall, and in terms of the competitors is actually as important as the prize amount as well. The other component actually is the time Like how long should we run the competition for? I always felt that we should be running, like we had a big debate, should this be a 3-week contest or a 6-week contest? And what we're finding, again, this is more anecdotal, is that there's a deadline effect. So people, will like everybody here, works to the deadline. So right, the night before, there's a ton of stuff going on. But there's also sort of diminishing returns to having it run for long periods of time. So we're actually running shorter contests, with 10K, 15K, 20K, 30K prize amounts, just to get the ball rolling and attract lots of people participating. Yes.
Was it open source? Are people building on each other's code?
No, this one was you're competing on your own. People could see a leaderboard that would show where you were in terms of performance, but the code was secret. The experiment I'll talk to you about, we had both of those kinds of treatments in there. Yes?
Have you also looked at what kind of tasks this works for? Because I hear you say what the crowd did basically in 3 weeks, but the crowd couldn't have built a big station.
Yes.
Have given that to them. So what kind of stuff does this work for?
So I think that's an open question for us. There's a company called Local Motors, which is building cars through crowds. So car design and so on is being, so the design that you saw at the space station, they're actually sourcing from cars from the crowd as well. So I think we're, for sure, when it comes to information products, we have seen crowds perform amazingly well. From Wikipedia to open source to this kind of stuff. What's interesting is that the whole world is going digital. The whole world is becoming an information product, right? Any physical object can be represented as, with this information shadow, and then we can then put it on the computer and let all you guys go crazy at it. This is actually what's so interesting, that in fact, as the entire world gets digital and cyberspace is actual real space, then these approaches are becoming more and more effective, I think, as well. In this contest, we had those 10 winners, but again, sometimes it's 2 or 5, depending upon what we're trying to encourage here as well. Yeah.
Why do you think there is a drop in the performance of the crowd? Do you think that's because certain people don't participate because there are only 2 or 5 winners? So if I'm an okay programmer, I'd probably be reluctant to play a game where I'm probably not going to win.
Absolutely. So I think there's a whole scale effect. There's a whole deadline effect. And then once you see other people doing really well, you're like, oh, I should maybe stop. So all those elements come into it. Absolutely.
There could be a mechanism to help those who are not the best coders kind of come into the system and try to get better?
Yeah, I think there's some work we're doing now in saying what happens if we actually limited the transparency of the signal being generated? Because right now, this is a public signal, right? Everybody sees your performance. Everybody sees how good you are, right? What happens if you actually limited that signal so only you had it, and then you could then and you had the option to turn that on or off? And that may, in fact, have some very interesting consequences. Absolutely. All great questions. Great, so let me move on. And just walk you through the paper in a quick nutshell, then we'll get into all the gory details. I'm going to take a very broad view. When we think about innovation systems, we think about the patent system, academic science, we think of open source. These are all what society has invented over time. And these are all systems designed to both encourage innovation. We want innovation to happen, so we create incentives. But we also want disclosure. We actually want those inventions to be made available for other people to use. In fact, in our Constitution, right, the patent system is part of the Constitution because the founders felt like we needed to create incentives for inventors, but also disclose those inventions. So these 2 components are part and parcel of how we think about innovation. And what we ascertain and we'll talk about is that what makes them different is really the timing of disclosure. So all innovation systems are in fact open. So even if you think about patents, right, patents are open because you have to publicly disclose your invention and how it got done. You just have monopoly rights over what happens to its use later on, right? Similarly in science, open science, right, you publish a paper, right? That's what gets disclosed, and that's what gives you accolades. And so the timing is what makes these things different, instead of just sort of this battles about open versus closed. And what we show in this paper is that a system like open source, where there's lots of intermediate disclosures, we're sharing code snippets, we're sharing intermediate advances with each other actually dampens incentives and participation. So we get, contrary to what I expected, we get lower participation, lower effort in these systems, yet we get higher performance. And we'll try to explain why that is going on. And we, in fact, see more experimentation, right, and more exploration in closed systems. And we'll explain why that may be going on. And the argument that we make is that there's a real convergence of technical paths that people follow in open systems, in intermediate disclosure systems, that enables them to get high performance. But this has implications for how we think about the knowledge stocks that are available to people and who's participating in these systems along the way.
You're talking here about competitive environments?
I'm talking about a competitive environment just because in innovation what happens is that in the end there are some outsized returns to what's going on. Absolutely.
Is less common in a competitive environment. These kinds of models tend to be very collaborative.
Exactly. So what I'll explain to you is our best attempt to not talk about open source versus open science, but to say what differentiates open source from open science per se, or from closed development, is the regime of intermediate disclosure as one element, right? That sort of says we can share what we've done right away with everybody else, and other people can build on that. So we use that as our sort of our treatment to say, how does that in fact happen to work out in a system where people are able to use anybody else's code and still retain some kind of rewards at the end.
Would you call something like Wikipedia intermediate disclosure?
Yeah, absolutely, because it's continually being built upon. People are disclosing different things. Although it's not an innovation task per se, they're just creating content. But that would be in the same line, absolutely. Okay. So let's just talk about these dual objectives for innovation systems. So the first is you want to offer incentives for inventive effort, right? So patents allow monopoly rights or use rights. Academia is based on funding, promotion, awards, and honor. And open source, there's use benefits, there's reputation, intrinsic rewards, and so on that come into it. All these elements are basically ways for society to sort of say, we want to reward inventive effort. At the same time, right, we want to ensure that inventions like the Google Glass get disclosed, right? That in fact people know how these things work, and that other people can build upon that. And that's the essential trade-off that the society makes. We want incentives for invention, but we also want disclosure. So patents, of course, you make knowledge in public domain. In academia, you're publishing or perishing. You got to publish, right? If you don't publish, you don't exist as an academia. You want to disclose what you've discovered. And in open source, it's sort of enshrined in the process. People are always making disclosures, and it can also be in the license itself. So these are the dual goals of all systems. And we think there's a false debate between sort of closed and open innovation. It's really, all innovation systems are geared to be open in the end, right? It's just a matter of when you enforce disclosures and what timing it is and what form they take. But everything that society does beyond, I think, trade secrets is geared towards openness. So we can get into a lot of sort of semantic battles about open versus closed innovation and what works better, but really the difference we argue is one about disclosure and when disclosure is happening. One format is sort of this final disclosure, right? So if you think about patents, a completed invention is put out there, right, for other people to consume later on. In academia, it's a published paper, right? We submit a paper, we do the experiment, we do the work, and we publish a paper. And in prize contests, some technology is developed that becomes available for other people to use. So we call that sort of final disclosure, which later allows people to then build upon and so forth. But the process is secret and not available for the people to participate within. In the world of intermediate disclosure, we actually have this setting where we're constantly making available our advances to everybody else. And a great example actually was the Human Genome Project. The Human Genome Project in the 90s, basically, once they were under attack from Celera, actually, in the race to sequence the human genome, they actually came up with this radical approach called the Bermuda Principles. They were in Bermuda for a conference, great place. And they said, any discovery that's made by any lab as they're sequencing the human genome will be made immediately available to everybody else, publicly disclosed. right? This violates the most principles of academic science because we keep our data secret. We keep our experiments secret, and we have a race for priority to publish our papers. And here they said, no, in fact, we're going to make everything available very quickly so people could then actually coordinate their activities and go after things that haven't been done before. Of course, in open source and the world that we live in, there's code fragments, advice and tips on problem solving, complete code. Everything is continuously being disclosed. And for me, I was talking to some of the students here before. Having been at the start of the open source movement when this stuff was taking hold, so our experience now of going to Stack Exchange and asking somebody for help and reading their solutions was not the default, right? Before, people didn't have those things available. We might have had Usenet available, if you guys know what Usenet is, as a solution. But that was not common. So all these things are, in fact, new in terms of behavior change in society, in terms of us being able to live with this. And certainly in the world of biology, there's biological repositories. You can actually get microorganisms and mice. Mice have code in them that people can share and use for their own experiments as well. But here we're actually, again, making intermediate products available for people to reuse. And what's interesting is that this is also a historically important process. So lots of studies now in the history of technology showing that the airplane, Bessemer steel, blast furnace technology, all those were based upon systems of collective invention where lots of people were sharing knowledge throughout, and teams of engineers, distributed teams of people were sharing knowledge back and forth to make this happen. And in fact, some work by Meyer, in fact, shows that all the US system was actually very open and open to sharing, lots of knowledge flows happening in the US. And once the Wright brothers came up with their invention, they were they were participants in the system. Once they came up with their invention, they actually started to patent, and the locus of activity for aircraft invention then moved over to France, where there were no patents on aircraft at that time. So if you think about words like aileron or fuselage, those are all French words because that's where all those developments were being done. And in the U.S. actually had a dip in inventive output for aircraft for a while. But this is the world that exists. And so we have within this setup this incentives versus reuse trade-off within our invention systems. And the key concern we have is balancing ex ante incentives. Can I encourage you to exert effort and spend time and money working on a problem, right? At the same time, come up with a system that says that the disclosures that the inventions you come up with will be available to everybody else. The worry is, in the economics literature, is that as you bring in greater disclosures, right, you will degrade incentives. People will not invest effort because they won't be able to appropriate those rewards for later on. Right? This is classical economics 101 in terms of as my use rights decline, I'm going to be less inclined to work. And what's happened in our society is that we create compensating mechanisms for greater disclosure. So we have things like priority and citations in academia that are worth something that we can use, and signing and authorship in open source, which says that there will be other rewards for participation other than direct use rights or monopoly rights that could be useful as well. And then also, we may actually attract different people with different ethos for sharing and so forth as well. And so that's how society has sort of dealt with this perspective. But incentives matter a lot. So we're in the Gates building, so I thought I'd use a quote from Bill Gates. So, in 1976, right, he writes basically a letter to hackers, right, saying incentives matter. Incentives matter a lot, and he built Microsoft, right, on this basis that proprietary incentives matter a lot. And we're the beneficiaries of this letter and what he was able to do in terms of innovation. But there's also the Torvalds perspective, right? So Linus Torvalds comes back out in the 90s, right? And he says, hey, do you pine for the days when men were men? Those were all men at that time, and were their own device drivers, right? Are you without a nice project designed to cut your teeth on an OS you can try to modify for your needs? I'm doing a free operating system, just a hobby, it won't be big and professional. I like feedback on things. This is a program for hackers by hacker. I enjoy doing it. Somebody might enjoy looking at it. Drop me a line if you're willing to let me use your code, right? So he's definitely on the compensating mechanisms for incentives and about sharing and reuse. And we are living now in this world of both of these institutions, at least in the world of software, coexisting, and people going back and forth oftentimes between them. All right? So this debate is not just theoretical, this is real. People make choices, make investments based on where they end up on this debate. What we know from research and economics is that more open, more access equals increased reuse. So the whole world of user innovation have shown that people, once you make technology available, people will reuse them and share them and keep using them over and over again. Of course, platform encourage reuse of components. You disclose those components, and then platforms grow and become really powerful because we've got those components available. And academic science has shown that basically future citation rates are a function of reuse rights. The more reuse rights you provide to people, the higher the reuse becomes. So it's a very obvious kind of a finding that we would sort of expect. But what's missing is the counterfactual. What we don't know is what happens when both the systems are in play and how do people actually work out. So the perspective I'm going to bring is that while we have a view about innovation in terms of incentives and reuse, we also need to think about innovation as a search process. You're searching for the best solution. And it's not just a production function thing where we think about incentives and outputs and efforts, but we actually want to think about this as a search process. And there's a broad literature in economics, in management, that thinks about innovation as a search process. And if you think about the search process, what you want to think about is there's some kind of a landscape on which you're searching for the best solution. And that landscape may have peaks and valleys, and you want to find the highest peak along the way. Yes?
Often the view of design is that design is not a problem-solving endeavor so much as a problem-setting endeavor.
Yes.
And I wonder what the innovation literature thinks of this. Like, where actually the thing is some very non-convex function where you just jumped over to something that no one even considered was actually going to be useful.
Yes.
But actually ends up solving the core problem in a way that.
Yeah, that's a deeply philosophical question. So the question is, do we invent the solution landscapes as we do the problem solving, or do they already exist? I don't have an answer for that. But I think that's I don't think the literature has looked at sort of invention, sort of endogenous invention of solution landscapes. I think it happens for sure, but I don't think we have an apparatus yet and the innovation literature to actually deal with that and to think about how that may come through.
I view this as like, we could have made a dumb mobile phone that has longer battery, but in fact we ended up with this very different problem, which was designing a handheld computer. Basically.
That's right. Yeah.
If you start with the problem saying, I need more energy efficiency or something, you never would have found that.
Exactly. No, and I think in my other work on contests, we actually think that defining the problem is actually a big part of what drives success. And so then there's some effort in saying we actually need problem designers, right, not problem solvers, right? Because if crowds can solve any problem, right, then we need actually really good problems to give them. And that's a whole different skill. And I think the D schools are the ones that are probably pushing the boundaries on that. I don't think management schools are anywhere near that perspective. Absolutely.
I wonder if this is, companies often feel like they want to be open to innovation, but it's hard to actually make that change if there's some very big leap that.
That's right. Yeah.
If we need to bring these closer together.
Oh, absolutely. I think that's a core element that I think needs to be worked on. Absolutely. Yeah.
And how difficult is it to share work in progress? Because I think that's also another deterrent, right? There are a few incentives, and B, it's just hard to give your work, put it out there and let others use it.
Yeah, so I'm going to show you a field experiment where we made it super easy, but the practicality is that it's actually there are transactions costs in sharing, right? We have tools available now for us to share more easily and more broadly, but it still is effort. Absolutely. So I'm going to try to take care of that to the experimental setting, but that's what experiments allow us to do. All right, so the element to sort of think about when we think about innovation as search is that the direction And pathway research activity is as important as as important a consideration, right? So this is exactly the point you made, which is like, you know, which direction are we going to go after? Are we going to go after sort of a low-end cell phone that lasts for 30 days, right? Or one that has 9 hours of life and then you're like scrambling to find the power? Those are choices that people make, and those choices can either be correlated or they can be independent. And that's the point we're going to try to address here going forward. And you know, there's again a big literature about innovation happening along pathways, trajectories, and paradigms. And the thing to keep in mind is that as we think about disclosure, right, we may in fact get either parallel independent paths or we may get convergent paths. And this is the big thing that we're going to try to unpack in our work. So there's been a whole bunch of formal mathematical models of search based on Simon's work and Kaufman's NK models. And what we have shown, the literature has shown is that in fact, you know, multiple independent search trajectories, parallel search is important to find high-value solutions to problems. At the same time, we know from this literature that communities of innovators tend to converge on paths. All right, so we need to be able to ascertain between them, and we want to think about concerns about local versus global optima. All right, so what do we do? I've got a bunch of predictions. They're kind of wordy. I just want to show you what we thought about in the paper, and then we'll get in the data. The first prediction we made is that in fact, in a regime where you have intermediate disclosure, we'll actually see incentives drop. People will not work as hard, will not participate as much, as compared to a regime where there's no intermediate disclosure. Our second prediction from the literature is that, in fact, we see you know, much more experimentation in closed regimes than in open regimes. And in, the third prediction is that in the open regimes, we see a lot of convergence. And the convergence and the performance will depend upon the stock of knowledge that already exists. All right? And so we'll try to show how these all three elements work for you. Okay, so what we did is we implemented a field experiment. It's actually tough for us to do this in the natural world because it's hard for us to compare open source to open science. Right? They're both open in wording, but very different sets of people, very different sets of outputs. It's hard to compare across them. So going to a field experiment setting is better because then we can control a bunch of things along the way. And what we try to see is what happens when we bring about a treatment of either intermediate disclosure versus final disclosure, okay? And see the causal effect of those things. We use the top coder online platform. We offered like $6,000 and 2 weeks. And we took a problem from Harvard Medical School, sort of a genomics problem, to solve this, to make this challenge happen. And what we can do is we can distinguish between technical approaches, and we have lots of microdata on entry, effort, their ability to peek on other people's solutions, and individual level data about who these people are. So what's the problem? So basically, you know, in genomics, one big issue is sequence alignment. You get lots of reads of sequences, and then you want to be able to assemble them together. Big problem. And what we're trying to see is, can we actually apply this to a really huge problem in immunology, where they're trying to do the whole work of immunogenomics, where the data constraints are, the data explosion is really huge. And the challenge was basically, can you annotate 100,000 sequences on a laptop, right? And you saw the details about the contest. So what did we set up? We had we announced this on Topcoder, and we have 733 people sign up to say, this looks like an interesting challenge for me to work on. I'm going to participate. And what we do then is we have great data on skills. I'll show you in a minute what the skills data we have, because skills are actually a really important control you want to have in any kind of analysis of crowdsourcing, because it could just be that we're attracting the really top skill guys, and that explains the performance dimensions right away. So we work really hard to make sure that we can in fact control for skills in all of our analyses. All right, so we took these individuals, right? We rank ordered them by skill, and then we took triplets of closely tied folks and assigned them randomly to, you know, an intermediate disclosure regime, a mixed regime, and a final disclosure regime, which I'll explain to you, right? And so basically, we had about 245 people assigned to these regimes, and then we had prize amounts here as well for getting the problem solved in week 1 and week 2. In the intermediate disclosure regime, what happened was you got the problem statement, and basically, in order for you to know how good your solution is, you had to submit the solution back to the system. And as soon as you submitted that solution back to the system, it made that code available to everybody else to use. Okay, so you got a score, but then your code anybody else can look at and basically reuse as they wanted to. We built in a citation system to allow for sharing of rewards, but we actually basically had that set up. In the final disclosure regime, basically nothing happened. Everything was dark, right? You submitted your code, you got a score, people saw your score, and that's it. And then you could keep moving on. And then we set up a mixed regime as a control to allow us to do 1 week of closed and 1 week of open to allow us to see for robustness testing.
Clarification.
Yes.
In the disclosure condition, my code was published, but was it also tied to my to my number?
To your number, absolutely.
Okay.
So you saw performance, you saw code, you saw identity. Absolutely. Yeah, all put together. And then again, so this prize pool, first place prize was $500, $250, $125, and so on. All right, and the disclosure regime was really one of click. So we just made it super easy, right? You just click on the thing, and you got the entire code base, and you could then see its evolution over time. All right, and then what we do is, we hold constant the problem, the assignments, the interface, the production technology at the time, the market signal, the top total purse, and the top 5 prizes along the way. In the disclosure regime, they could. In the intermediate disclosure, they could chat. In the other regime, they couldn't.
Monitored.
Yeah, I don't use that in my analysis, but we have that available to us as well.
The disclosure regime, is there anything preventing me from just plagiarizing existing?
No, you could take it all.
And like, will I get like?
You could if you kept doing it, and you could get the top prize if you wanted to.
Okay.
Right, that's just like open source, right? You could take somebody or go to GitHub, press copy and paste, and be up and running.
Yeah.
So you can imagine, right, what's going on. This is exactly the underlying question we have. Like, if you implement a disclosure regime like this, where it's available right away to everybody else, what are the incentives going to be? Right. Okay. So just in terms of the overall performance of the system, it actually rocked quite good. So let me just show you. So again, we had 733 signups, 122 people actually submitted code. We uncovered 89 different approaches to solve the problem. Okay, so not only do we get high numbers, but we get diversity, which is actually really important for innovation. Winners from Russia, France, Egypt, Belgium, and US, right? People that, the medical school didn't know existed and could never even hire, right? For many reasons. And, basically we got down to being able to sequence, 250,000 sequences in 1 hour on a laptop, right? So pretty awesome results. But let me show you the results graphically. So our scoring function had two elements. One was time, how fast were you able to do this? And the second was accuracy, all right? 0.8 is the theoretically accurate, the theoretically maximum accuracy you could get from this data set, all right? These are all the submissions that we got from our folks, the green dots, and this is a log scale, all right? So, we want to be here, basically. This is the NIH Megablast solution, and this is the code from the Harvard researcher who volunteered to give us their problem. So, he's no slouch. He's a good colleague of mine, undergrad from MIT, PhD from Oxford, is at Beth Israel as a pathologist and a computational biologist, and has a lab working on this problem, right? And oh, by the way, none of these guys have any background in computational biology, right? Because what we did is we took the problem from biology and made it into a math problem, a computer science problem, and then these guys could go at it. Yeah.
How are you identifying the differences? Like,
I'll show it to you in a second. Okay. Yeah. It was manual grunt work. But done by somebody else, not by me. Okay, so who signed up? So again, we had all these people, 733 people show up from 69 different countries, okay? 44% of them were professionals, and 55% were students, either PhD or master's or undergraduate programs. So a lot of these guys here maybe show up. Was that? Exactly. And then, sort of on the younger side of the population distribution, but that's not a surprise, right? By the time you're in your 40s, you're busy with kids and all that kind of stuff, and you may not have the options to work. And then also, a big distribution of skills, all right? So top coder has an ELO-based skills rating, which looks at every person and looks at their history of competition, and based on that gives them a metric of skill. I think I might even have it, yeah, right here. So we can see here, this guy, he's from Brazil. He's a red-rated coder, and you can see his performance in algorithmic matches over time, and he's here. So really on the high end of the distribution in terms of performance. So this is generated. ELO is a way that chess grandmasters get evaluated against each other, and they've implemented the same system for programmers. So we have a good sense of the skills of the individuals participating with us. Okay, so what do we see first? I'm just going to show you some pictures to sort of drive home the point. There's no fancy econometrics here at all right? So one is lower participation overall, right, in the intermediate disclosure regime, right? So you can see both in terms of number of active entrants and the cumulative number of entrants, who shows up, right? And there's and I'll show you some more results in a second to show you some p-values. But just from this, you can start to see, that incentives matter, like your question. And as soon as you're in a regime where, for the same sets of people, where you change, when you bring in more disclosure, you will have actually less entry. And again, this was contrary to my bias. My bias was that open more participation. But in fact, we're seeing the incentive story kick in here. The second thing is hours worked as well. And this is by skill, big difference pretty much across the distribution in terms of people working on the problems, all right? So fewer people enter, they exert less effort. And overall, what we find is, participation rates are about 26% lower in intermediate. Number of submissions are 56% lower, right? And hours worked are about 30% lower, okay, overall. So people are putting in time, but still, it's quite important to sort of see at these regimes. So when we see open source and this great mobilization open source, there's got to be other things going on beyond just the real incentive effect of participation. Yes.
There's less time that could be due to reuse.
Exactly. So I'm going to show you that exactly. So what we see is that what happens is that one could make the argument from our data that open is more socially efficient, right? In two ways. One, you allow for reuse, right? And secondly, you actually, because we have this dropout, right? People are being allocated in the economy better, right? Because I see you participating, he's a hot shot. I'm not even going to show up because there's no way I'm ever going to be able to, to improve upon what you've done. So that may also be going on as well. Okay. All right. And then also the problem-solving performance was higher in intermediate because of this reuse effect, which I'll show you, than in the final. And average score was 1.6 points higher, controlling for skill and effort. So we basically have a whole lot of controls here in the regression that allows us to basically show, and 1.6 actually makes a difference between being top or not overall. So this is quite interesting for us to see as well. All right. So you see a story coming together about what's happening in a world of disclosure. And the question you have, when you're in a world of being able to look at other people's code, people are peeking a lot. People are looking at code and learning from it and in fact doing it. So we have about I believe close to 1,000 incidences of people looking at, because we could see when they clicked on this code here, and then in the mixed regime, it's flat, of course, in the first week, and the second week it again takes off. Most of the peaking occurred in the first week where people were looking at the code bases and trying to understand what the best paths were. Okay, so what explains these results? How do we actually make sense of these results? So the first thing we want to understand is how do we actually discern the solution paths, right? How do we actually figure this out? So what we had was we got a top coder participant, per rouleau, to in fact look through the code bases and see what were the elemental techniques being used by the programmers themselves. So he made an inventory of basically sampling a whole bunch of submissions across the distribution and saying what's being used. And he came up with all these different approaches. So basically 10 distinct elemental approaches being used. And then we had other top coder PhDs, one German and 2 Chinese, to go through every submission, right, and say, are they using this or not along the way, okay? And then what we do is solutions are a combination of techniques, right? So it's basically a bit switch 1, 0, 1, 1, 1 up to 10 different ways to do that. And you can then look at how unique are those approaches being put together. So it's a manual effort. We weren't smart enough to sort of somehow computerize this effort, but it got us a really high level of fidelity to do this. So basically, you would sort of see, you see here, this was our sequence alignment project. This is the coder. This is his 8th submission, and you can see his code, and then you can see what's going on in this code. All right. So paths are consequential. All right. So what I'm showing you are 2 graphics. This is performance versus combination of approaches, and we're just basically rank ordered them, right, by average score within the approach, right, and the number of people that did this. And we've transformed the score here as well. So what you see is that some paths have a really low score effects, and some paths have really high. Okay. And the second thing we see is that the number of elemental techniques you use to solve the problem are in fact consequential as well. So the more techniques you use, the higher the average score. Okay. So both things matter. And what's interesting as a counterfactual for us is that when we look at what Megablast had done, or what the Harvard research had done, we were really like orders of magnitude more than what they had done in terms of the approaches they had considered. And here we see the entire landscape basically coming through. The second thing, I just want you to sort of look at this picture and say the search patterns are very different, right? So in the world of no intermediate disclosures, you basically have this gyration going on. People are going up and down, searching up and down, up and down, up and down, right? Versus here, it's very much sort of a smooth progression to the top. All right? Yeah, this was the guy who came in the last minute, copied somebody's code and submitted it. Literally, that's what happened.
And so were there more influential codes? So like for the intermediate disclosure, were there a few that people kind of modeled theirs?
Exactly, and I'll show you that in a second. That basically the intermediate guys were able to basically find the high-performing code. You had access to those code, and then you could just boom, go crazy at it. Versus these guys were blindly searching. All right, they had a score function that they could compare themselves against, but that's it. But they didn't have access to anybody else's knowledge to be able to do anything with it. Okay. And so what we see is that there were 30%, what's interesting is that there were 30% fewer novel techniques in an intermediate disclosure. Simply because, they just found the cool stuff and they went right after it, versus these guys are exploring much broadly. And these points, these lines, if you put them on the same graph, never cross, right? They're always, the closed no intermediate disclosures regime is typically just heads above in terms of experimentation that's going on. And we have a Herfindahl index of the submissions, and you can sort of see that there's much more homogeneity, concentration here than here. Okay? And then what we can also look at is number of high potential novel approaches versus low potential novel approaches considered. And again, what you see is that the closed guys do much more exploration on the low end of the potential approaches. And the open guys are pretty much on the high end. Okay? So what's happening, right, is that in the world of intermediate disclosure, people get access to other people's knowledge, right? And if you have a performance metric available, you can then take that and go crazy and improve upon that, right? But that's at a cost of less experimentation, right? Less exploration, right? And less participation. And so we have to be able to balance between those things. So, again, in intermediate disclosure, fewer participants, less effort, yet higher average and maximum performance. Vast majority of people will peak and reuse. So of the 32 people that were in our open disclosure regime, right, 30 of them actually did the peaking and reused. It's available. Why wouldn't you use it? Search behavior, more experimentation, more exploration in the final disclosure regime, and convergence and coordination over the best paths in intermediate disclosure. But this has consequences for us. Yes?
Exactly explain the fewer number of participants.
Incentives, right? Because this is the fact that some guy at the end is going to come in and steal my code and run off.
Okay, but
Okay.
if you have intermediate rewards, that should somewhat take care of it, right?
Somewhat, right? And so what we're doing is in our experiment, we're trying to make the difference really sharp to see in fact what's going on. And as I'll discuss next, what we have in other systems are compensating mechanisms, right? Allowing you to actually get rewards for credit and so forth along the way as well. Okay, so the thing we need to sort of think about is that increased reuse, right, comes at a cost of lower incentives. And it's highly dependent upon the stock of knowledge being created, right? Because the stock of knowledge, if the stock of knowledge created is not that great, we're going to be in trouble. Convergent and coordinate behavior, relies on the stock of knowledge available. If that's no good, then we won't get the best solutions. And the potential concern that we have here is that the fitness landscape may in fact be driving some of this behavior. So we chose the problem almost blindly, right? So we were working with the medical school, they were highly skeptical of this approach ever working for them, right? So we said, you know what, we'll fund an experiment, right? We'll raise the cash prizes and you just find us a cool problem. So we found a cool problem in computational biology, right? Now it may have been, right, that basically the problem was like this, right? So one single peak, you find the solution and you go, boom, you go after it, all right? And everybody can share it. But if we're in a world of rugged landscapes with lots of peaks and valleys, right, we may be in a different world, right? This requires broad experimentation. This requires broad search, right? Which the closed regime did. And so, one of the consequences of the study is that, in fact, the choice of problem you have, can actually should then determine the disclosure policy you're actually following, right? We should.
You have the solution.
Exactly. So we need some more work on trying to understand what kind of problems are these. Could there be corner solutions, or is it just one smoothly increasing approach? Absolutely. So this is ex post analysis and thinking about it. Absolutely. So there are comparative advantages of the different systems, right? So you would use an image disclosure when there is a broad stock of knowledge already available for reuse, right? So one of the things that open source has shown is that Linux did well because we understood the Unix framework, right? That was not a mystery, right? And that allowed people to then take that knowledge and then build upon that and elaborate amazingly well. Same thing with Wikipedia. But if we were starting a brand new operating system, Herd didn't go anywhere for some reason. If you guys know what that is, but a brand new, completely novel conceptualization may have problems because of these effects. The diversity of participants, we argue, may overcome this local optima concerns that we have. So, we in our study we can control for skill and sort of actually take away the diversity that exists. But in fact, in the real world, there may be different perspectives, and open source and open communities may in fact attract lots of diverse people, and they may not get locked into these perspectives. Again, empirical question for us to go after. And of course, this compensating incentives, right? That there may be other benefits to participation above and beyond the final outcome reward that we're set up, and that may drive participation as well. All right. In the final disclosure world, useful when you want broad-based experimentation, right? And this is really the startup economy that we live in, right? What you guys are so aware of here in Silicon Valley, right? So if you think about social media and the explosion of social media, right? There were probably about 1,000 companies trying to do what Facebook and Twitter eventually got done, right? The 998 of them died and went away because they were in the low part, and 2 or 3 did really well and did amazingly well. So our economy is set up to actually do this parallel independent search, depending upon the problem that we have in front of us. And again, this is the insights that you want to start thinking about here. And even here, in terms of final disclosure, in some of the work we're doing on contests, the emphasis that we have can be on implicit incentives, participation incentives, and not just on explicit incentives, and that can also drive behavior. So like when we do these contests where, if we have 1,000 people participating, and most of them are losing, right? There must be other benefits to participation, and we again see that in the setup. So I'm going to end with, every HBS professor has to show a 2x2. That's in our contract, So I'm just going to show you like a 2/3 by 2x2 or something like that. One is a missing element. So what you want to think about, right, are two dimensions, right? Emphasis on disclosure of intermediate advances, right, versus emphasis on disclosure of final innovations, okay? That's one dimension. And the other is property rights and exclusion versus disclosure, right? What are you putting together? So our industrial innovation system, market-based systems have a process which says we give you property rights and exclusion if you disclose your final products. That's where we're at, right? Academic science and public innovation contests are really geared towards emphasizing disclosure, but only of final products, okay? There's a lot of controversy in science right now that, people should list out all their data, right? There's a study out recently that apparently 70% of biomedical research can't be replicated, which is kind of crazy, right? And so but we're in a system where, you never get the underlying data set. You basically get the tables and the graphics, right? So this is the world we live in. And then what we've seen, so clearly in the last decades has been the Human Genome Project, open source and user innovation communities, open data, open APIs, biological repositories, all of these guys pushing for disclosure of intermediate advances. And I think so that's how we're set up right now as sort of our major institutions for innovation. And what's interesting for me is to sort of say, as a B school prof, like what are firms doing? And if you think about a company like IBM or like Google, they're actually playing in all three dimensions, right? So IBM, the biggest patenter in the world, right, also does a lot of scientific research that they publish, also is the biggest contributor to open source, right? Google, big contributor to open source, scientific research, also patenting, right? So in the economy, we have firms figuring out, either through some master plan or just trial and error, living in these three regimes. And I think the question for us as academics and scholars is to sort of say, is this the right way for this particular problem, right? Or should we be thinking about alternative ways for us to put together? So what's amazing as a researcher for us right now is that we can now run these counterfactuals on real problems with real people and then get these types of results. So I think I'm almost out of time too. So questions, thoughts, comments? Yes.
Whether there's like some way that you could, instead of doing like just all of the problems are available for you to look at, you have some system which like characterizes, which essentially builds a model of like, suppose you looked at your logs and then like you basically looked at the amount of innovation that results, and then like you like whenever people look at solutions, and then like you can say like, for example, like people, you might conclude something like after looking at more than 2 other solutions, then at that point in time, like the benefit of looking at additional ones kind of decreases off, right? And then, have you considered building a system that kind of selects other people's solutions to disclose to you? So instead of giving you like, here's all the solutions, in which case all you'll do is just look at the top ones. The top ones. Instead of that, it basically selects them such that it attempts to maximize your solution diversity, right? So like, suppose you're able to do that characterization live, right? That bit pattern of strategy is used, and then basically said, okay, we have none of the solutions we generated have used this particular bit pattern. Yes. We want someone to generate it. Yes. Well, let's try and like select some, and then just present it to them, and then hopefully they'll just like click and then like generate a new solution. Like,
yeah. So I think it's a great idea. We haven't. It's hard to do because to know in real time what the approaches are, and would require some of your smarts to help us along the way. Certainly, some of the things, a colleague of mine at MathWorks, at MATLAB, they actually run this sort of intermediate disclosure contest all the time. So basically, they have two days of closed and then 5 days of open. It's just for tchotchkes. There's no cash involved. And Ned there has actually said that he's tried to build systems where you could signal to other people saying, here's a novel bit of code in here that hasn't been tried before. and get people to sort of raise so even though it may score really poorly, there might be a novel bit of insight that somebody can grab and do that. Because, to be a programmer, you need to understand both algorithmic things, but also need to think about efficiency and how fast you are and that kind of stuff. And some people may not be good at both. And certainly when we've done an analysis of the MathWorks code bases, we actually see sort of, you can think of the code is in a cassette, right? And there's some little gems inside of it. And the question is, can somebody find those gems, grab them out there, and then go with it? But we haven't built up a system with that. I think that would be very meaningful.
Have you thought about trying to look at different processing strategies for problems that have less well-defined criteria, like problem formulation? So propose policies that the CDC should consider for reducing AIDS transmission in this community or that community. Consider strategies of water desalinization, where you're trying to generate a problem that is well specified enough that it could have the usual metrics, but you're trying to explore the problem characterization.
Yeah, so that's a great, so, what you've hit upon is, in doing this work, I think the solutions are easy. It's the problems that are now the constraint, like how we define the problems. And there's no, I think maybe the D schools have some insights, but at least from my perspective, there's really no science or problem formulation that exists right now that we can actually take and replicate. We know that matters. I've got a doctoral student graduating right now, Hila Lifshitz, who spent a year at NASA looking at problems, not these computational ones, but really hard ones like, how do you reduce microbes on the space station, right? And how do you formulate that problem, right? Because right now they send, liquids up to the space station, and it's $10,000 per kilogram for up mass, so it matters a lot. And how do they actually do the problem formulation? So I think problem formulation is actually the next big thing that those of us that are doing crowd research are going to be focusing on. We did this interesting thing with the medical school where we said, and I have a little practitioner paper out on this, where we said, if you think about research, it's completely vertically integrated, right? The PI and the lab decides on the interesting hypothesis in the question, comes up with a proposal, sends it to the NIH, right? Their peers in the same community evaluate, and then there's some possibility of getting funding and working away. What happens if we actually disaggregate that process? What happens if we actually open up the hypothesis generation process? So we did that with type 1 diabetes, where we basically said, you don't need ability to solve the problem, you need to come up with a really good question. And we have a paper on that trying to understand how those processes work as well. And then we did the same thing on evaluation. We said not just the close experts, but in fact a whole range of people in the medical sciences can be evaluating. And then we actually did more work where we said, let's take these hypotheses and generate new teams of people that have never worked together before as well. So that's the bleeding edge, and we're trying to understand that. But I think the insight about problem formulation is actually critical, because we can now with a credit card get answers, really good answers, really fast, and then it's a matter of like, have you asked the right questions? And the finding we have is the question you ask is the answer you'll get. Like it's so, these guys are so like there's nothing else but they go, this is the question, this is the evaluation metric, great, I'm going to give you the answer on the way.
So if you look at the people who actually create the innovations, right? So it's like the first person to have passed a threshold, like some threshold score at some time t, right? Have you looked at like I assume you log like which other solutions people have looked at, right? Like, have you looked at like approximately how many other solutions you need to look at before you're able to like, on average, before you're able to like achieve like an innovation? Is there like some magic number or so?
That's a great question. I haven't, not in this context, I haven't looked at that. There's another paper I'm working on right now where we look at, is your ability to invent related to your ability to copy? Okay, so invention capability and copying capability. So, and what we're finding is that you become a better inventor as you copy more. So the quality of your inventions are better once you've learned, and this effect runs both ways. So as you invent more, you're better at copying as well. You find better stuff to copy as well. again, from an econometric point of view, this is a hard study for us to do because you've got all this endogeneity going on, and we have a bunch of controls and fixed effects and so forth to deal with that. But we feel pretty comfortable about this finding that, in fact, there's a virtuous circle between invention and copying coming together, right? And that's the society, right? People, there's no sort of lone geniuses. You're embedded in a world of other ideas, and from that you formulate something coming out of it. And that we use the MathWorks data for to actually get at.
Can you speak briefly about your tracking of like the rate of innovation? So we look at like what's the marginal impact of each coder, right? And even looking at that over time, right? Are there bigger leaps initially than there are later on, or so on? Can you speak briefly about kind of what you've seen there?
Yeah, I think that's really a function of the problem itself. So what we find is an asymptote, right? Like basically, initially there's lots of big things, and then it's harder and harder to eke out the performance gains. But I think that's more us being unaware of the solution space that exists, right? We sort of see it instantiated as people work away. And this is a debate that we have. Like, is 2 weeks enough, or should we have 5 weeks? Because what we find is that 2 weeks may be actually enough to get you way further ahead, and there's no need to spend another 3 weeks working on the problem as well.
So I'm wondering, under the closed regime, if you look at the distribution of strategies that people use, you argue that there's some correlation between the strategy and success.
Yes.
And I'm wondering whether there's an effect of how many people center in on that strategy. Do people actually know which strategy independently is going to be successful or not?
Yes.
And I can translate this to another domain. We teach courses here in like interaction design.
Yes.
Last year, a surprising number of projects dealt with finding bathrooms on the Stanford campus. And I'm wondering, does that signal that this is a really important need, that if we built this, everyone would start using it?
Yes.
Or is there actually less signal there than you might think? That it's maybe an obvious thing to design for, and yes, a meaningful solution, but not a global optimum.
Yeah. So I haven't looked at so at least the data that we show is that there is more diversity in the strategies being used by people working blindly, right? And so that in itself is a good outcome for innovation, because we want diverse experiments to take place. So the answer would be we don't see correlation in search strategies once you're blind, which sort of makes sense, right? You sort of have your own idiosyncratic knowledge. And given the types of people we attracted, they weren't all from Stanford. They're from around the world, different backgrounds, different training, and that's what probably drove it.
So my question is, if a bunch of people independently all agree that this Levenstein distance strategy is the best one, does that mean it was the best one?
Yeah. You're asking a lot of philosophy questions. Yeah, I think absolutely. Yeah.
It was.
Yeah,
so
yeah,
if
yeah.
people piled on.
Yeah, people piled on. That made a difference. Yeah, absolutely.
Okay.
Yeah, absolutely. Yeah.
So could you imagine them using a combination of both final disclosure and intermediate? Because in the final disclosure, you want to get all of these, like all this knowledge and build it all up. But at some point, you could imagine convergence is helpful.
Yes.
So is there
Absolutely. I mean, I think if we can somehow figure out the right way to incentivize people to do both, or that you attract different crowds, I think that it depends on whose perspective are you taking, right? From a social planner's perspective, this is what you might do. You might say, I want lots of diversity initially, then I want convergence, right? Then I want more diversity, and this is like design thinking, right? Like you want diversity, then you want convergence, and you want diversity, and you want convergence.
And that's what a lot of big companies do now.
Yes.
All of them. Initially, they're just exploring, but once they come out with something, then they want others to start converging to that. Right?
Absolutely. Right. And the question is, can we sustain the broad exploration in our organizations? Right. Typically, in most of our organizations, for any problem, you might have one team, maybe two parallel teams, but that's it.
Yeah.
Right.
Final question.
The intermediate group, you say that the best one actually has the best code, but the other competitors have been proved that they learning more than the other group that, for example, could be the best one of that group that wins the task, but the others didn't learn anything because it was always close.
Yes, I mean, I think the learning question is a really important question, and I don't have good answers for that. Because I mean, I think it's hard for us to be able to judge what they might have learned. They looked at somebody else's code. At the end of the contest, all the code was available to everybody else to use. Are the skills and so forth. So that's a really hard question. I try to find easy questions with easy answers.
Okay, let's thank our speakers.
Thanks a lot. Thank you. Produce such robust quality software. And again, I've looked at issues about motivation, self-selection, and participation, and now doing increasingly more work around partner selection and for collaboration through field experiments as well. And in many ways, these two institutions are diametrically opposed if you sort of think about it. In the one case, you're basically running a winner-take-all contest where people are competing and rushing to solve a problem. And the other setting, you have communities. People are sharing knowledge, they're learning from each other, and they're collectively improving the overall perspective of the code being produced and the overall performance of the code being produced. And for me, this has always been a puzzle in terms of what's the better way to organize ourselves? Should we, when we have a creative task, when we have a software programming task, when we have a scientific task, is it better for us to set up ourselves in communities and collaborations, or is it better for us to set up contests and competitions? In many ways, I started here. This I was actually kind of allergic to when I first started paying attention to this during my dissertation time, because I drank the open source Kool-Aid, and I just felt like that was just a great way to organize work. But as these became more and more popular and powerful, it required attention to say, like, what's going on here, and why are these equally as effective as this? And that's what the puzzle I'm going to try to solve over the next time we have. The work I do is part of what's called the NASA Tournament Lab. It's a research lab funded by NASA to help us understand how these types of open innovation perspectives can be put to use for government agencies, but for innovation in general. And so what we do is we work with NASA, we take their toughest computational challenges, and then we crowdsource them through platforms like Topcoder. I've also done a bunch of work with our medical school in the computational biology side of things, where again saying that in fact we can take computational biology questions and also get them solved through contests and communities. And in addition, a bunch of work, let me just hang on a second, and a bunch of work around how we actually organize collaborations in the medical school setting. So if you look at the Harvard Medical School, we have it's fun to be in a cross-disciplinary group. So basically, I mostly talk to economists and sociologists, and then to talk to people that often are subjects of our studies is actually really, really fun. Stanford, just as a person though, Stanford is near and dear to my heart. My mother in the 70s left Pakistan to come to Stanford to do her master's degree. And that enabled us to immigrate in the early 80s to Canada. And it was really the Stanford education that really set us up for where we are today as a family. And it's always had a soft spot in our hearts. And of course, when I was considering graduate school, Stanford was on the top of my list. And somehow MIT kept winning over every single time. But I'm super happy to be here and to present this work. This work is in collaboration with Kevin Boudreau, my good friend and co-author at the London Business School. We went to MIT together as PhD students and have started to work together on a bunch of these kinds of questions. And so what I'm going to talk about, you saw the title, I keep changing the title around to make it more simpler. So this is the new title, how disclosure policies impact search and open innovation. I'm going to explain to you all of this as we move forward. I just want to give you a sense of my research and how it all fits in. I've been thinking a lot about how crowds get organized and how we can get productive work from crowds. And there are really two major institutions that we see out in the economy that enable us to work with crowds. The first setup is competitions and contests. And in this work, I've done a bunch of work to sort of explain who wins and why, what are the bases for performance in these settings, why people participate, and behavior in contests. And I've done both research using archival data, looking at Innocentive and Topcoder to pull out these results, and also field experiments. And we'll walk you through a field experiment soon. The other way to set this up is actually through a community. So everybody's aware of the open source software world and what that's done. And I've in fact started my research first there to say, how does open source work and why does that on the back end side? In terms of the reward size?
Yeah.
That's on the high end for Topcoder. Topcoder projects are typically much smaller than that. They'll be like $500 or $1,500, but those are for more software components. These are longer term projects, 3 weeks, 4 weeks, and so on. Of course, as we'll discuss later, there's beyond just the prize money here. Get your code assessed by NASA, having your name on the wall, and in terms of the competitors is actually as important as the prize amount as well. The other component actually is the time. Like how long should we run the competition for? I always felt that we should be running, we had a big debate, should this be a 3-week contest or a 6-week contest? And what we're finding, again, this is more anecdotal, is that there's a deadline effect. So people, will like everybody here, works to the deadline. So right, the night before, there's a ton of stuff going on. But there's also sort of diminishing returns to having it run for long periods of time. So we're actually running shorter contests, with 10K, 15K, 20K, 30K prize amounts just to get the ball rolling and attract lots of people participating. Yes.
Was it open source? Are people building on each other's code?
No, this one was you're competing on your own. People could see a leaderboard that would show where you were in terms of performance, but the code was secret. The experiment I'll talk to you about, we had both of those kinds of treatments in there. Yes.
Have you also looked at what kind of tasks this works for? Because I hear you say what the crowd did basically in 3 weeks, but the crowd couldn't have built a big station.
Yes. Yes.
Have given that to it. So what kind of stuff does this work for?
So I think that's an open question for us. There's a company called Local Motors, which is building cars through crowds. So car design and so on is so the design that you saw at the space station, they're actually sourcing from cars from the crowd as well. So I think we're, for sure, when it comes to information products, we have seen crowds perform amazingly well. From Wikipedia to open source to this kind of stuff. What's interesting is that the whole world is going digital. The whole world is becoming an information product, right? We had actually had 2,000 signups. It was quite incredible. NASA can be a big draw for people to participate. The winners are here. So Italian, Chinese, Polish, Chinese, Estonian, Chinese, Canadian, Chinese, and Belarusian. Yes, exactly. What are you guys doing about it? So this, so we get broad engagement and really cool code. Of course, NASA cares about how good is the code, right? Does it actually do anything at all? And what we have here for you is the final output of the code submissions that they had for how much power output you can get based on the configurations that they predicted. And this is sort of solar power output. And then this is every single person that had submitted in their final submissions. Now, some things you'll see immediately is that there's actually quite a bit of bunching, right? People have done really well. And in many ways, sort of the differences between the first and second are not that great. But then here's the NASA solution, okay? And depending upon how you model the NASA solution versus our solutions, we either exceed or meet what they've done, all right? So in what was, multi-year, multi-X millions of dollars of projects that they do to get this kind of information out, we were able to basically get done in 3 weeks for 30K. And this becomes a very compelling way for us to think about organizing creative work if we can actually take these very tough software problems that require lots of people and lots of attention and say, can we actually get it done this way?
How do you choose 30K?
Random. So in fact, that's a good question. The prize size is in fact still an art than a science. What we're finding is that too high a prize, and that'll actually deter entry because people think the problem is too hard. But you want to actually reward people for their efforts as well. So we've been typically in these types of projects in the 10 to 50K, depending upon the problem and what we're trying to get done. I have 20,000 researchers, about $1.5 billion in funding from the NIH, and three campuses that are far apart from each other. How we find collaborators and partners is actually a big, big question here, and that's part of our research agenda that we also pursue. So let me give you an example first of a contest we recently ran for NASA for the space station. So let's have a look.
Energy, in one form or another, powers everything on Earth, and the man-made things floating above it, too. This is the International Space Station. You've probably heard of it. It's powered by the sun, and the sun's energy is captured by the station's solar panels. Ensuring the space station harvests the most energy possible is a complicated task. Why? Well, for one reason, see those large solar panels? Holding them to the station are very long, thin arms called longerons. Anytime an odd number of longerons are in full sunlight, with others in the shadows cast by the rest of the space station, they bend, and eventually break. For this reason, ISS operators are careful to position the station to limit shadowing, and so only an even number of longerons are shadowed at one time. However, this conservative positioning reduces the power the station can collect from the sun, thus causing inefficiency. NASA wants more power for the ISS. More power means more science and cool stuff that NASA can do on orbit. NASA needs a sophisticated algorithm, and they think you just might be the key to this whole equation. Introducing the NASA Tournament Labs International Space Station Longeron Challenge. Your solutions just may help power the International Space Station and allow more science from more scientists around the world. Consider this your invitation to blast off with NASA. For more information, visit topcoder.com/ISS if you've got the right stuff.
So this ran in March, 30K pool of cash available to solve this problem. It was a 3-week-long contest. Here's what we got. We had broad engagement, 459 competitors submitting about 2,000 code submissions.